In this video, we're going to take a look at some of the equations which we will be using in this course. Most of the equations that we're going to look at now are introduced on page 6 of the relativistic dynamics section, which is the second section in the book. This first equation that we're going to look at for the Lorentz correction factor is introduced in the first section of the book, which is relativistic kinematics. So we'll be talking more about where those equations come from when we get to those sections in the book and talk about relativity, but we will occasionally see some of the equations in other sections of the book before we get to relativity, so we're going to talk about them now. I would suggest that you start making an equation sheet and put down some of the equations that you're using when you do your homework, and that way when it comes time to take an exam, you'll have all those equations in the same place. And I would add the equations that we're going through now to that equation sheet. Okay, so we have the Lorentz correction factor, gamma, and it is equal to 1 divided by the square root of 1 minus v squared over c squared, where v is the speed of the object and c is the speed of light. The smallest value that you could have for v is 0 if the object is not moving. So it's being squared. You just use the speed of the object, not the velocity of the object, so it doesn't matter whether the velocity is in the positive direction or the negative direction. So if v is equal to 0, then for the correction factor we have gamma is equal to 1 divided by 1 minus 0 if v is 0, which just gives us 1. And the fastest speed that the object could be going at is the speed of light. So that would be if you're talking about light itself or a photon, then we could have v equal to the speed of light, in which case gamma, the correction factor, is equal to v squared over c squared would become c squared over c squared, which is just 1, but now we have 0 in the denominator, so the correction factor goes to infinity. So for this correction factor, you can have anything between 1 and infinity. We did not see the correction factor in any of the equations that we looked at in Physics 161, because in Physics 161 we are only looking at classical physics, where objects were not going anywhere near the speed of light. And if your object's not going anywhere near the speed of light, you can try doing this on your calculator. V squared over c squared is going to be very, very small, and so the correction factor is going to be very, very close to 1, which means you can approximate it as just being 1. Okay, so that's why we didn't have to use the Lorentz correction factor in Physics 161. For most of the problems that we're going to see for the first sections that we're covering in the book, objects are not traveling close to the speed of light, so we're going to look at that when we get to the relativity chapters in the book. So usually the correction factor is going to be close to 1, and if you want to check to make sure that you don't have to correct for the fact that something's moving fast, you can just check to see what the correction factor is, and if it's close to 1, like if it's 1.003, then you can treat things classically, at least with regards to relativity. Okay, so now in problem 42, you're going to be using the classical definition for momentum and the classical definition for kinetic energy. But we have different ways of comparing momentum and kinetic energy in this course. In problem 42, from nuclear physics, we have the momentum is equal to the mass times the velocity. The kinetic energy is equal to 1/2 m times v squared. We have an m times v in the definition for momentum, and we have an m times v squared in the definition for kinetic energy. So we can relate the momentum and the kinetic energy. One way we can do that is to write the momentum in terms of the kinetic energy. So I'm going to say the momentum is equal to, I'm going to need to put a square root in here because I want to use the kinetic energy, but the kinetic energy has a v squared in it. So to get to m times v, I'm going to have to take the square root, but I only have one m here, so I'm going to need another m. And I have a 1/2 here, which I don't want, so I'm going to put a 2 there. So if I do 2 times m times ke squared, that's m squared times v squared. I take the square root, that gives me the momentum. Okay, so I think you will be seeing that in problem 42. And this is using the classical definitions because in problem 42, gamma is, the correction factor is very close to 1. Okay, so now we're going to talk about the equations that appear on page 6. So, relativistically, we can't say the momentum is equal to the mass times the velocity. Instead, we have to put the correction factor in here. So if your velocity is not really close to the speed of light, this is approximately what we had back in Physics 161. However, there's something else that we like to do with momentum in this course, and that is to multiply it by the speed of light so that the units for our new quantity, which is p times c, will be the same as the units for kinetic energy. So going back to what we have here, this is mass times speed squared, so that's mass times speed times speed. So if we take this momentum, mass times speed, and we multiply it by something that has units of speed, then kinetic energy will have the same units as our quantity here. So this is just momentum times the speed of light, and that, you will see if you're looking at page 6 of relativistic dynamics, can be written as gamma times mc squared times v over c. So we multiplied by c, but then we put an extra c in the numerator and a c in the denominator, which is a useful way to write this quantity, because, as you may be familiar with, we have E is equal to mc squared, but this is only the rest energy of the object, so we will have to be careful about that, because oftentimes people just say E is equal to mc squared, but it's the rest energy that we're talking about when we use this equation. So this Pc is also equal to gamma times the rest energy times V over C. So E is the energy that the object has when it's at rest, and V is the speed of the object. Gamma is the correction factor, which we saw up here, which also depends on the speed of the object, and C is equal to 0, and it should not surprise you that if the velocity is 0, the momentum is also 0. That agrees with what we saw in Physics 161. Okay, now the equations get a little bit more interesting. We said that the rest energy was equal to mc squared, but if an object is moving around, it has kinetic energy also. So we have E total is equal to the rest energy plus the kinetic energy. So this is kinetic energy plus the rest energy, which I'll write as mc squared. Okay, so you take the rest energy, that's the energy that the object has even when it's at rest. You add to that any kinetic energy that the object has, and you get the total energy. Then the total energy can also be written as gamma times mc squared. But we can take these two equations and we can then use them to write an expression for the kinetic energy. So from this equation here, I have kinetic energy is equal to, if I bring the mc squared over to the other side, that's E total minus mc squared. And then if we put this expression for E total in, we have gamma mc squared minus mc squared, which would be gamma minus 1 times mc squared. So there's a lot of different relationships here. Oh, and then one other relationship that we have, this is also on page 6. E total squared is equal to PC squared plus MC squared squared. Okay, so when we're talking about total energy is not equal to mc squared unless the momentum is 0. If the momentum is 0, the object is at rest and the total energy is equal to the rest energy. Oftentimes we will write this equation as E total is equal to the square root of PC squared plus MC squared squared, and then you can see if PC is equal to 0, E total is equal to MC squared. Because in that case, if the kinetic energy is equal to 0, because the object is at rest, E total is just equal to the rest energy. Okay, and then as a device to help you remember these relationships, we can do the following. And what I'm going to do now, there's also a similar figure in the folder on the M drive, and it is called relativistic energy. Okay, so this is just a device to help us remember these equations. We're going to draw a right triangle, and I'm going to say that this side of the triangle is PC squared, and this side of the triangle is MC squared. And then I'm going to draw part of a circle that has a radius of MC squared. So that would bring you, maybe supposed to be a part of the circle. Okay, so then this would also be equal to MC squared. I'm going to call the hypotenuse of my triangle E total. And then from my equation here, E total is equal to KE plus MC squared. So if from here to here is MC squared, then this extra bit here must be the kinetic energy. So from looking at the hypotenuse, we have E total is equal to the kinetic energy plus MC squared. And then by using Pythagorean's theorem, we can say the hypotenuse E total is equal to, whoops, this is just supposed to be PC. This is equal to PC squared plus MC squared squared, and that would be the hypotenuse squared. So those two different relationships, if you draw this triangle here, that's just a device to help you remember those relationships. Okay, so like I said, some of these equations may be popping up in some of the chapters that we do before we get to relativistic kinematics and relativistic dynamics, so we'll talk more about what those equations mean when we get to those sections in the book. But for now, you have these equations, so if you need to use them or if you see them in example problems in lecture, that is where they are coming from.